Hello there, this is Rick Haynes. We are ready to start the webinar. Hope everybody's ready. Well, we're all here to listen to a little discussion about using Minitab and dealing with bad data. This topic came about because teaching the students, I've got this question about 6 times in the last month, which was really a lot. What we're going to talk about is what I'm calling bad data. It's really a reason to introduce the reliability and survival methods in Minitab. I'm going to be doing my work in Minitab 15. I believe 14 is identical. 2 of you have talked to me about using possibly version 13, and I believe it still works that way, but I don't have a copy to check it. I'm going to do a live demonstration. So what you're going to see is this real time. You have the ability to add questions in. Please do. I won't be reading them as I'm going along, but as soon as I finish the live demonstration, I'll look at them and answer what we can. I guess that's where we're going. Again, I'm Rick Haynes, Master Black Belt and statistician, work with Smarter Solutions in Austin. I've been doing Black Belt for as long as it's been around, it seems like. Started my training in the late 80s. And right now I'm an instructor and consultant, and I'm just going to talk to things I've learned along the way. I hope you all get something from it. You should have all got a data set that was in version 14, and I forwarded 2 copies of version 13 out. You probably don't want to do it along with me, but you have the ability to if you want to, or maybe after the fact. Being that all of us are here to learn how to do this, this is not a commonly used technique. Practicing it will help you. I think your goal should be to realize when you can use this tool, then go figure out how to do it again. So the goal is not to be an expert, just to see what you can do. That's it, I'll start. So what am I calling bad data? Bad data is really when you get a data set given to you to work with, but you can't use it all the way. Either it's not accurate, it doesn't represent what's really happening, and I'm going to talk to 2 reasons that can be. Not measurement error, but excessive rounding we'll talk to, and then data collection errors in general. And bad will be when you can't calculate a mean and standard deviation that represents the performance. And you can't really do a capability study, and we'll talk to some of that as we go through the data sets. First one's excessive rounding. I see this often when systems collect cycle time data or lead time. When you really are pretty good, you're running the 2 to 3 day average. But what you get is your data set says, how long did it take? Well, it took 0 days, 1 day, 2 day, 3 day, 4 day, and that's about it. So you can't do a lot because it really looks like discrete data, but you know that it's continuous. So we're going to talk about a way to process that data to get an accurate mean and standard deviation set. And if it's log normal, which it may be, how to do a capability analysis on it. Another choice is when you're using a gauge that does not have the resolution you need. It only gives you 3 to 5 or so values, so you can see each step or increment in your gauge. It's very hard to deal with that. So that's what we're talking about there. That's our first example. Next one's data collection errors. 2 of them is the most common one, probably is material property testing or really reliability testing, where you've got numbers up to a certain point and then they don't record anything. One of my students who is also listening today, I guess she's certified, but she came and that's what the data had. It came values up to a maximum and then they reported greater than some value. How do you deal with that? Now the control charts and the capability analysis all look odd because you don't really have real data for all of it. Another case is in chemical testing and such when you have a minimal detectable number, where it reports all real values down to a certain number and that's the lowest it gives. How do you deal with that? So that's what we're talking about. And the last one's misrecorded data. This example came from one of the students about a year ago that because of a fixturing and measurement, all the values in the middle of the data were listed as 0 that shouldn't have been, and we'll talk about that too. These are all real life times that you would lead into reliability testing tools. Now as we dive into this, I'd like to know a little about the audience. I did see from the list there's a lot of people that I've met, but we're trying to get an idea where you are. It may help me decide some of the sides or side tracks I take in given this. So you got a minute here, please check on the box on your screen where you are. I see a couple of you doing it. Looks like a lot of us are practitioners and some other stuff. And a couple of you haven't seen much. Now I'll admit this seminar will be going a lot at Minitab, but the concepts are good. We'll close it up here. Most of you voted. You should be able to see what happened now. As you see, most of you are practitioners. And spread across the rest of them. Great. I think you'll all get something from this. I think we're ready to go for the next step. Okay. What is the reliability in traditional sense? What really this whole set of statistics was created so you could handle data where you didn't get all of the information. I'll talk a little bit about light bulbs or equipment failures. So if you're trying to estimate when the average lifetime, if you don't realize that those light bulbs you buy in the grocery store have an average lifetime on it, they use these tools to calculate that. Or also you'll see it in the mean time between failure, or MTBF, in the maintenance group if you do collect that. Generally they come in a Weibull, log normal, or normal distribution, but really you can use any distribution. How this stuff comes about is you really, in reliability testing, like the light bulbs, you put them on, you run them till they start getting failures. Say we have 100 light bulbs. We turn them on, they time them when each one fails, but if you wanted to get the real average, you'd have to get an entire 100 light bulbs. And if you're like me, some of those light bulbs seem to last forever and some go out quick. To keep you from having to wait to the end, they have created these tools so you get a significant number of them have failed, and then you can estimate the true mean and the standard deviation of the data set even though you haven't tested them all. Now, how many do you need? Well, I use the word representative because there isn't a real number. You get what you can. What Minitab or other statistical programs will do is they know you've got so much data, but they know that some percent of the data or events haven't failed after a given point. So it really uses a probability testing to figure and fit a distribution to it. Many of you may not realize you're using it depending on where you may have learned your Lean Six Sigma work. But when you went to the stat reliability and survival in Minitab and used the right sensor data, you were using this tool already, but not using the function of censoring, which is really where we're going to go into today. I hope this gives you an idea where we're going. Now we're going to do a live demo. I'm going to cover 3 sets. Simple right censored data, such as the light bulb example. We'll do interval censored data, which is where some of the real power leads, which is the lead time or the integer days. And I'll do a little misrecorded data one if there's time. It'll talk about, this is in the middle of the data when the data was recorded wrong, how you can correct for it. We'll be playing with Minitab, doing a couple things. Again, type in questions as they go. I think I'll cover a lot of them, but anyway I miss, we'll cover at the end. Ready to go off the Minitab. Again, this is version 14. I'm going to check here to see if everybody can view it. Let's see. Not everybody's up there. I got a little thing here that tells me how many screens have updated to actually see it. I got a couple percent left. All right. We're almost there. What I'm going to start off is with the first 2 columns of data. What I have here is the actual data, and I have a column called censored. This is a case where we were measuring the time it took to do something, and at 14 days we quit collecting data, or 14 hours. This could be peel strength testing. You're measuring the strength to pull something against a specification, say 3, or a minimum of, let's say a minimum of 5. And after you know it's above 14, you quit taking the data. Well, what is your capability of the strength? So we're going to go look at it. All right. First of all, let's look at the data. Okay. I'm going to go to the graphical summary to show you what it looks like. This is the actual data. You can see the numbers. The histogram doesn't look real nice. It comes up with a mean of right about, let's see, 11.4 and a standard deviation of 3.5. What is the capability of being above 5? Let's go look at it. I can go to the quality tools and the capability analysis, normal. It's actual data, subgroups 1. I'll put a lower spec of 5 in. If you look at this, now let me go do this one more time. I wanted to change it to percents. If you didn't know you could do this, it's under the options. I'm not sure if this is in version 14. I know it's not in 13. But it gives us here in percents. I have 3.5% predicted it'll be out of tolerance, but in the data set 10% is. The reason they're that far different is because of this bar right here, which was all the values at 14. Okay. Look at a probability plot also in case you'd want to do that, and you'll see one of the problems you get here. You may have seen this before. It looks like it doesn't fit real well. Now, what can you do? Well, that's what we're going to talk about, and that's the point of this. Okay. First thing we're going to talk about is right-censored data. Let's look at it. What the data is it's got numbers up to 14, and then they're just 14. Okay. We're going to go to the stat, or reliability and survival, right-censored data, and a distribution ID. Now, where right-censored comes in is the time scale. The values we know are actuals, and then we're going to give it an indication that anything above a given point is censored, meaning we don't know where it goes above that. So I'm going to put in my actual numbers here. I'm going to go to censored. I'm going to pick the column that I have, which is censored, and I'm going to say, if you look at it, I'll show you in a second, 0 was the values of 14. I could have also put time censored in there and put a 14 in there, but this is my favorite because you can see it. I'm going to look at only at these 4 distributions. If you look at it, those are the 4 that you generally see for reliability testing. It's also the 4 you see most in a Lean Six Sigma program. Now, if you look at this, you see the 4 probability plots. You would generally pick the one with the highest correlation coefficient. Log normal and Weibull both look very close. Now, I happen to know that I picked this as reliability data. It's probably a Weibull, but we can do either one. Once you get to this point, what you do is then you go back and do the parametric distribution analysis after picking one. I'm going to pick the Weibull right now because that was reliability data. If this was time data, I would pick the log normal just because I know it falls in that typically. Reliability survival, right censored, but we'll go down to the third one, the parametric distribution analysis. Put the same data back in. Put the censored. Put a 0. I'll leave it Weibull, which is the default. It gives me a probability plot. Interesting things here. Notice the dots only go up to 50%. Right here. You can also see over here it's got a shape and a scale, a mean and a standard deviation. These are estimated from what it believes the distribution is, not from the actual data. Notice there's 50 points that are real and 50 that are censored. So half of them are 14. Okay. I can use this to estimate my capability to meet 5. I will add a percentile line, the data value of 5. This says 7.2% of the product in the future should be below 5. This is different than it used to say before, which was 3.5%. This is a better estimate. All right. I hope you got what you need out of that. That's the basic way to do reliability testing. It's also how you can make a good estimate of the standard deviation and what the data really means. Now, if I wanted to, go do something with this, you can then make a probability plot in the normal method using the shape and scale parameter, the Weibel, if you choose. All right. I'll show you how to do that in the next example. So I'm going to go to the next data set. Again, if you have questions, I know I'm going a little bit fast. If I didn't say it, you're all going to get a link to a white paper or a technical paper that walks through this with all the venues and has a better discussion of it so that you can refer to it later if you choose. We're going to go to a more general case now. Go to the other data set. This was the first one. Notice the zeros were at 14. In this case, I have a data set that was given to me. Call this lead time data in the days it took to process something. And I'm told to go estimate the capability. In other words, it's got to be, let's say, 10 days or less is what we'll look at. Well, how good are we? Well, first thing we can do is we'll look at a probability plot of it, of the rounded data. It looks like this. Well, that doesn't look so good. First of all, you've got granularity. Also doesn't fit the line. It is obviously not normally distributed. But it's cycle time data, so let's try a log normal. That's the common distribution for time. A couple of you already know what's going to happen when I hit this button. Can't use it with positive data. There's zeros in there. All right. So what are you going to do? That's this is probably the best part of the topic. We are going to change the data so we can do something with it. First of all, we're going to get to something called arbitrary censored data, or as I learned it, called interval censored. This is the generic form for all the reliability testing. Most people don't touch this in a black belt or any Lean Six Sigma course. Okay. We're going down to distribution analysis arbitrary censored. I'm going to start with distribution ID just to show you something, because I do this often and I still forget how to do it. But notice how the menu changed. Instead of a data column, it asks for start and end. So it's talking about an interval. Well, to remember how to set it up, I'm going to press the help button. Minitab has wonderful help screens that go to data, and it's got a really nice discussion here of how you enter data for this. Now, I hope you can read this. It might be small, but I couldn't find a way to make it bigger on my screen. It gives you 4 different types of data that you could enter into this function. If it's an exact value, we're going to create 2 columns, and you'll have the same value in both columns. As you can see in the, let's see, there's got to be one here if I look down the data. Right here, the one 50,000 and 50,000. That's an exact point. Now, there's right censored, which we just did earlier. In that case, you'll see we put a real value in the start column and an asterisk in the end column. That means telling Minitab the number is between 90,000 and infinity for this. Now, there's left censored, which means you know that the answer is somewhere less than the value you know, the first row. 10,000 would be end and an asterisk for start. So it means the data, the true value, is to the left of 10,000. And then interval censored, which is the one we're going to use here, you put a start and an end, which show the interval that the true value falls in. All right. Now let's look at our data. I have rounded data. It's got 0, 9, 3, 3. First question you always ask the person who gave you the data is, what's a 0? Well, the answer you typically get is a 0 means it happened in the same day. So your data collection system must have taken start day and end day and subtracted them. Great. So a 0, what does it really mean? Well, a 0 really means the true value is somewhere between 0 and 1. Now I could go down the whole column and do this. A 9 would be, it took somewhere between 9 and 10 days. But we'll use the calculator instead. So we'll go to the calculator. We'll create a start and stop column. First of all, start will be my rounded value alone, because I know a 0 means that's the minimum it took. Now I'll calculate the stop, and I will add 1 to this. Oh, I just made a mistake, didn't I? So you get with a live webinar, I wrote over it. You got to change the start to stop. Now add 1. So now you can see I've got 2 columns, start, stop, and I show the interval. So a 9 means it's between 9 and 10. To use this tool, you create the 2 columns. We'll take an advantage of the third example. We will do it with just a couple data points. Now to do the function, we'll go back to reliability and survival, arbitrary censored, we'll do a distribution ID. I've got start, stop. I'll specify I'll just take those 4 again. And I look at my plot. Now what do you notice here? Well, first, there's not many data points. Minitab will plot 1 dot for each value that exists uniquely in the data set. And it keeps track of the probabilities of how many events you have in that case. Now which one looks better? Looks like log normal's got the largest correlation coefficient, so that's the one we would use. So I go back to the same arbitrary censored, go to the distribution analysis, put start, stop, changes to log normal, and there I get a probability plot. Looks real nice. I can say if my maximum value is 10, I put 10 in. What's it tell me? 93.6 below, or about 6.4%. Oh, it looks like I'm getting ahead of you guys. I apologize. I'll look at my little thing. Get it. All right. Hope you're keeping up. All right. So that's what you can do. Now, how would you do a capability analysis? Well, we just did one. You can't really use this tool. Now, if I was going to go do a control chart of it, which would be a predictability analysis, I'll shrink down my graph. Is my process stable? Well, you would go to a control chart, individuals chart. I'll do an individuals. My rounded data. You see it's got an out of control point, but you'd also notice it's got a natural lower limit. Something doesn't look right. And if you were trained, the next thing you'd do is do a transformation of the data. Some of you know what's going to happen anyway. I have a feeling the screens are updating slower than I'm talking, so I'll slow down a bit. If you have the box talks turned on, it'll give you an error. Why? Because there's zeros in there. Last thing I'll cover is how could you do a control chart of this? What we'll end up doing is add a half, because really each interval of 0 really means between 0 and 1. You can use the calculator. We're going to call it charting. We're going to add 0.5. So this is the middle of every interval. Now, how would you figure this one out on your own? Well, once you realize that a 0 is really an interval, you can go through all this step. You should see now you've got 0.5 for the zeros and 9.5 for the nines. I can go right back now to do my control chart for an individual's chart. Instead of the rounded data, I'll put my charting data. The box-Cox transformation is still turned on, and I get a very nice control chart now. My process is stable. Therefore, with this information and the prior probability plot made with the arbitrary censoring, I can make a capability estimate. I now have a baseline to move ahead. Now, if this was your project, I will assume that you also realize you have to change the data collection. If you're going to do much with this in the future, you're going to have to measure actual time rather than integer days. All right. That was one. I'm going to go through the last one now. Again, if you have any questions, please type them in. No one's done one yet. The last one's a little more, I guess, more real in some respects. This came out of a company that made windows. They're measuring a dimension. It's in the one called dimension. And what I've noted here is the true values with 1 or 0. What they found is they were rounding their values up. Anything between 0 and 0.5, they recorded as a 0. Let's look at it as a histogram. You can see right here, there's a dip. Now, most of us wouldn't worry about that. We'd say, that looks close enough because that could be random variation. They really noticed it when you do a probability plot, though, of this data. Normal. See what happened? This is what triggered the black belt to say something's not right. There's a gap in the data. When he went back and checked with his folks, this is what they found, is that, well, those were really zeros, but they couldn't fit the measurement device in because of a fixturing issue. Now, how do you adjust to get the real numbers? Because right now you realize the average will be off because things that are really between 0 and 1/2 are recorded as a 0. We're going to use the same concept we did in the last example to go show you how you can use the arbitrary censoring to estimate the true values in the database. All right. First thing we have to do, though, is create 2 columns. Well, the dimension's a true value, but really every 0 is somewhere between 0 and 0.5. I'll show you another way to go create the second column here. It's one of the neat functions Minitab does that you can't get many places. It's called coding. We'll do a number to a number. We're going to code dimension. We're going to create a new column called maximum. How's that? If there is a 0 in the column of dimension, we'll call it 0.5 in the second column. Everything else will copy over the same value. I'm going to move this over because Minitab puts it all the way to the left so you can see it better. So here I have the data. It put the exact number across, and when I have a 0, it put a 0.5. So this again uses that data. If the same number is in both columns, it's an exact number. If they're different, it's a range. We will go to Stat, Reliability and Survival. Again, the arbitrary censoring. And this time I want it to be a normal distribution. I'm going to go right to my distribution analysis. Hit F3 so it clears everything out. My start is my dimension column. My end is my maximum that I just created. I want this to be normal. Hit OK. You'll see it gives a nice probability plot now. The data actually follows the middle of the line now. And it calculates the mean is -0.02 and a standard deviation of 1. Well, when I created the data, I knew it was a random numbers with a mean of 0 and a standard deviation of 1. The prior set, what did it have? It's still pretty close before, but it doesn't look right. All right? Well, that's the difference. This is a minor change. But again, I was just trying to reinforce what you can do with the tools. Before I walk away, that was really the end of the live demonstration. I hope you could follow. I saw that some of it was slow. The screen updates, that is. I'm trying to see if we have any questions in. What is rounded? What I mean in rounded data from the earlier part, rounded data is where when you get the data reported to you, it doesn't have all the significant figures that they rounded it already for you. They may only give you the total number of days it took to do something rather than the number of hours it took. Or if you're measuring the length of something, they only gave you inches and not tenths of an inch. I hope that helps. But the idea is you know that the truth has got a lot more resolution, or it's on a continuous number line, but the way they gave it to you, it looks like it's a series of unique numbers, and when you look in the probability plot, it looks like a picket fence. Oh, there's more questions. How do you suggest we avoid these errors in our data collection planning? Well, that's a great question. Probably the best way to start is you tell everybody to write down every number they have on every gauge they use or display. Because some of them flicker on digital gauges and stuff. And people get used in the practice of work to only record the numbers that are about the same size as the specification or requirement. If you ask them to do all of them, you're more apt to get everything, and that way Minitab has a better shot with it. So really you just tell them to write down every number. Another one that's a great one that comes up is I had a student 6-7 years ago. They were doing a project to reduce the time it took to input drawings, draftsman drawings in an electronic system. They were running 18 to 20 days, and they only recorded integer days. Some were longer, some were shorter, but they had a nice capability system. The measurement system showed they have less than 20% measurement error, but his goal was to get it to 2 days. And when he went through and looked at, what will it be if I leave this data collection system? I'll have a 2-day average, which means I'll get 1, 2, or 3. I can't do a capability analysis on that. Can't do a very good control chart. So part of his project was to improve the resolution of the measurement system. And basically he just had the data collection, instead of recording day, also record time. By doing that, now he got a better data collection system when the project finished. So there's two sides of it. One is the first time, but also you realize at the end of your project you need to put a control system in place. Consider what rounding may occur at the end of your project. I guess that's all the questions. Let me finish up with the last slide here. Again, you'll get a paper talking about this. This was not intended to teach, but really to expose you to what we were talking about. So I talked about bad data. I hope you get a feel for it. It's data that isn't quite usable, but you can fix it with these tools. In the Lean Six Sigma world, we don't do an awful lot of reliability work. You may get called in to do it because you have Minitab, but the tools are really beneficial in these other areas. And I'm surprised, like I said, about 6 times in the last 2 months it's come up with students. That's why we're here talking about this. I hope you got what you were looking for. We'll probably do another one of these in the future as topics come up. Now, as you exit the webinar, a survey will pop up. Really appreciate it if you answer the questions. It's not too much. It's about this webinar and possibilities of doing more. Thank you very much for your time.